let's start with a look at the syllabus. What's today? Today is the 18th. Which means it's our last day of talking about I squared C. Thursday would be high voltage control, motor control, chapter 14. It's fun stuff. It's fun stuff. And it's really a lead-in directly into 388. Now, how many, do you guys take 388 next semester or 368 next semester? Okay, everything we've done, applicable next semester. You just apply it. So it's not like you don't forget this over summer break because you're going to come back in the fall and you're going to need to apply it immediately. Okay, and then next Tuesday, review for exam 3. Next Thursday, exam 3. May 2nd, last day of classes, makeup exam. Makeup exam is only if you have missed an exam. So today's lecture is going to be focused again on building up a library for the DS3231. Okay, am I recording? Yes. The DS3231. This is what you're going to be using in your final project to make an alarm clock. We've talked about SPI. We've built up a bit of a library to talk to the 7-segment driver, okay, using SPI. So we got to talk about this a little bit more. Now, last class we did talk about the DS3231 a little bit. This is the module that you're going to get. It's got 5 pins. It sticks right into a breadboard. 5 pins, ground, VCC, SDA. What does SDA stand for? It stands for Serial Data Line. DA, data line. SCL, which stands for Serial Clock Line. And those are the only 2 lines you need to supply. It also has 2 extra pins, one called SQW, square wave, and one called 32 kilohertz. 32 kilohertz is not the only output this will make. It's up to you to look in the data sheet and figure out what's going on there. Yes?
In this data sheet, certain things have a bar over them. What does that mean? Like AM, PM, 1224.
Well, what does a bar usually indicate? Think back to 260. Negated. So AM bar / PM, if it's a 0, it means it's AM. If it's a 1, it means PM. That's all it means. And actually, you know, when you get right down to it, if you look at these bits right here, as if it was an upper nibble, it's the same thing. It's either the 20th bit, or sorry, the 20 place, you know, that's all there really is to it. So no matter how you look at it, they don't like do some different kind of decoding. AM is 0 to 12, and PM is not. So that's the 20th hour. So what we got to do, we got to start building up some library functions for this. Last class, we had gone ahead and built a few library functions for a generic 2-wire interface. Okay, and let's colorize this with C. So this is, you know, back where we were at the end of last class. We had written a few functions. Let's look at all of them for a second. So this is it. We had 4 functions: TWI init, TWI start, TWI stop, and TWI send. Init was solely responsible for initializing the peripheral. We even wrote ourselves a cutesy little macro here that would give in the system clock frequency and the desired baud, and the prescaler would tell us what we needed to put in the baud rate register. And enable it. That's really all we did there. This is setting the prescaler bits to be a 0, 1. And remember that this is 2 to the power of the prescaler. So that where we have, 4 to the power of the prescaler. So this is 4 to the 1 is 4. We could have made one more macro to do that. Interfacing with this peripheral is just telling it to create something and then waiting for a particular bit to be set. Does anybody remember what bit gets set anytime anything happens from last class? We're always looking at the interrupt bit, the 2-wire interrupt bit. So anytime that goes high, something has occurred. And based on what we set in our control register here, we say enable it, write a 1 meaning start something, and we write a 1 to the start bit. That causes a start condition. And then we wait. We poll. This is a polling approach. This is not an interrupt-driven approach. The status register, once this bit gets set, once the 2-wire interface bit gets set, the status register tells us the result of that. And I've got a comment here. If you return an 8, that's a successful start. It returns a 10 if it's a repeated start. Likewise with stop, it's very similar. The only thing we do is enable and write the stop bit. We don't poll for the stop bit. That's the only thing in the I2C interface we don't poll for. Send is the most interesting one. We first put our data into the data register, but that does not immediately begin transmitting. We have to tell it to begin transmitting by writing a 1 to those 2 bits. And we poll, and there is a status. If you troll around in the data sheet for long enough, you'll find this diagram, figure 22-12. It tells you what things can happen and what your return values can be. So, assuming everything goes correctly, okay, you start a full transmission here with a start bit. Let's zoom in on this. A start bit, and your status register will return a 08. SLA stands for slave address, and the last bit would be a write. Then you get an acknowledge, which means the status register will have an 18. Then you'll send a data byte with an acknowledge that returns a 28. Okay. And finally, P is stop bit, which doesn't return anything. You could, instead of a stop bit, you could start another transfer with a repeated start. And like I just showed in that comment, a start gives you an 8. A repeated start gives you a 10. And then there are all sorts of things that can go wrong. So for example, you send the slave address, but you don't get an acknowledge. You get a not acknowledge, and that would return a 20. This is a very useful diagram in terms of what it tells you, because it tells you exactly what to expect. This is actually easier than consulting this table. Okay, this table does tell you everything you need to know, but in terms of following along while you're debugging this hardware interface, this is a little bit nicer because it's easy to see at a glance all of the numbers you might receive in your status register. So as you step through, eventually you would pause, for example. I'd set a breakpoint. How do I set a breakpoint? Set a breakpoint right there on those 2 return lines. Okay, so I would be able to access my status register anytime something had happened. So I'll call something, and I'll look at the status register at that point. And I'll look at that status register and I'll say, okay, what number did I get? And let's say that I was sending something and I received a 30. Okay, I picked that number randomly. What does a 30 mean? Well, I have to start looking, and I say, all right, 30, 30, 30, 30, 30, ooh, 30. That is a not acknowledge received after a data byte has been sent. Okay? More interesting ones that you might get from time to time, 38 means you lost arbitration. What is arbitration all about? Control of the thing is broad enough that it could apply to any question I had asked, yes. So it's control of the bus. This is with SPI and with I2C, we have a bus. The bus is a collection of wires that talk to many things. So who gets to control that is arbitration. So if 2 things are trying to talk on a bus, they have arbitration. Whoever is usually talking to the lowest address wins that arbitration. There is also another figure here, master receive mode. If I go down a little bit further, oh, much too far. This diagram, if you're receiving data, things are a little different, okay? Because now, instead of a write bit, we're sending a read bit. What's the difference between a write bit and a read bit? Okay, when we're writing and reading, one is a 0, one is a 1. But after that first initial start bit, everything changes. When we get an acknowledge for a read address, it's a totally different number. Which is why when we wrote our routines, we just return those low-level routines. We don't care if we're in master mode, slave mode, all right? We basically ignore that. So now we can begin writing some new functions, okay, that deal with the DS3231. To start with, I'm going to include TWI.h, that file that I just wrote. This would be TWI.c. We'd also have a TWI.h. What do we put in our H files and our C files? Why do we have two different files for the same information? No? Nothing? Different boards falls under the category of modularity, which is why we create libraries. The reason we put it in two different files, we have non-executable code in an H file, so it can be included as many times as you want. Executable code only goes in one file and it gets linked in. Okay, so we would include that header file. That way we can use TWI init, TWI start, TWI stop, and TWI send. We want to be able to use those functions in our library for the DS3231. So, okay, let's see. What do we have to do? We have to be able to, well, let's look at the data sheet and find out. Here's the DS3231. At its basic, we're really just talking to addresses in this device. How do we do that? Well, does anybody remember how we choose what address we're talking about from last class? We had started talking about it. Okay, there is a register pointer inside of this. If you have not perused this data sheet yet, I highly encourage you to do that before you get to lab, because you need to know how to use this device. So we have a address pointer. And the first thing that we can do to set the address pointer, I'm just going to start writing some code out here. Set the address pointer. We're going to have to do the following. We're going to have to create a packet, start. Helps if my keyboard, my fingers are on the right keys on the keyboard. Then we need to send a slave address plus a write. So I'm going to say send. I need to get the slave address. And in order to do that, I need to find the slave address in the data sheet, because I don't remember what it is. Do you remember what it is? This would be a great time to shine. Let's see. Address. We're looking for slave address. The address decode register. Valid I2C address. Come on, where are you? It's not here. Well, what do I do? Well, if I can't find it real quick, those of you who have a computer, oh, here it is. It's 1101,000. So I'm going to remember that as a 6-8. And I'm going to need to say a 1 for a write. So that's a 0. What I just did there was I took the DS2331 address, shifted it over by 1, ORed it in with a 0. Why did I do that? Because of the way the slave address packet works. It's going to be 7 bits of address and then the read-write address. I could have made an extra function to do this, and we might abstract that out later. Okay? But that says we're going to write to the DS3231. And we're going to then do another send now, and that send is going to be what address we want to deal with. And this is an example of a basic write. We're going to write what address we want to talk to, and then we're going to send as many data bytes as we want. All right. So we want to send a particular register value. And if I go back to that register map, where are we? Oh, maybe it's down here. There it is. So here's our register map. For any particular address that I want to talk to, I can do that. For now, I'm just going to say X, because it's just some placeholder value. Set address pointer to X. That will set the address pointer. That's all we have to do. The last step would be TWI stop. Now, in each of these cases, these are all blocking operations. They will pull the I2C flag, the TWI INT flag, until something happens. So this will take quite a long time. I am not going to be covering an interrupt-driven approach, although with the diagram here, you could actually do an interrupt approach pretty easily. You just have to keep track of what state you're in. So that's a basic idea to set up the address pointer. That's all we do, though. If we then wanted to write to things, okay, it gets a little bit more complicated. Where's my, I'm in the wrong data sheet here. The data sheet is very clear about how we have to do multi-byte writes. I got to get all the way back down here. When you want to write to things, you have to, it's always going to be a random access write. First, you write the slave address plus the write bit. Then you write the address you want to overwrite. And then you write n data bytes. This is actually pretty nice in the way they've shown it to you. The gray boxes are stuff that the 328P will be sending. The white boxes are things that the DS3231 will be sending. Okay, yes?
So those days in between are acknowledges?
Yes, and you'll notice if you look at the data read, they do sometimes send not acknowledges. Okay, and we'll talk about why that is in a moment. The details are in the data sheet as usual. But so if we wanted to do, so that's one piece of the puzzle, setting the address pointer. If we wanted to do a single byte write, just a single byte, this might be a function now. We'll call this one DS3231 underscore single write. We're going to be writing to a particular address, and we're going to have a particular byte of data. All right. So what do we have to do? Well, we just follow along with the data sheet. Here is what we must do to do a data write. Now, this is for many bytes, but 1 byte is just as easy as many bytes. So what do we have to do? Well, to start with, we got to set the address pointer. So I can copy that right out. And then what do I have to do? Well, now I've gotten my address pointer pointed to the right thing. Now, the thing that I want to point to is actually address, so it's a little bit different. Instead of X, it's address. Then I need to send another command or another packet with my data. And then finally, because this is just a single byte write, once I'm done, I send a stop bit. Or I guess I should say a stop condition. So that's enough to send 1 byte, single write. How would I send multiple bytes? Well, multiple bytes gets a little bit more interesting, not because it's different. If I had multiple bytes, I could just say data, I could call it data 1, data 2, data 3, data 4. Okay, it's nothing extra complicated here, just writing more bytes. But in terms of getting that data into this function, why am I unable to delete this line? Getting data into the function is a little bit more difficult, mostly because we're in C. So to deal with that, I'm going to write another function called multi-byte write. Multi-byte write. Now, I'm going to be writing multiple bytes. So I'm going to take in a pointer to an array of data. Okay, we're getting more into C constructs now, a little bit farther away from hardware. The higher your levels of libraries, the more you'll be focusing on C concepts than on assembly and microcontroller concepts. And probably I'll do something like a count. So doing this with a count now gets a little more interesting. Now I'm going to say for I equals 0, I less than count, I plus plus. Send data sub I. Not a big change, as long as you have a good concept of C iteration in your head. We're going to pass in an array of data. An array is just a pointer to memory. And we're going to say, this is how many bytes I want you to transmit. And it'll run this send command that many times. And at the end, it'll stop. That's really all there is to this. Now, these are not my final forms of these library functions. Once I get done with some of this, I'm going to start looking for commonalities that I can refactor out of the code so that I have a little bit less duplication. Okay. And actually, I think I might have, yeah, that looks pretty good. Let's look at reading now. Reading is a little different. We'll contrast them for a second. If you look at the comments here, when you're writing, first you must create a write condition with the slave address, and then you set your pointer, your address pointer, and then you write as many bytes as you feel necessary. When you are reading, you just say, okay, I want to read. Oop. Come on, I'm having trouble highlighting things. You just want to read, and then you start receiving bytes. That's it. Question?
Is the acknowledge all automated?
The acknowledge is the 9th bit. So you notice how when we're doing a write, the acknowledge is actually from the slave to the master. We're kind of ignoring it in our library routines. That may come back to bite us later. Okay, something that would be indicate. How would we even know if we were acknowledged or not acknowledged? How would we know that? It's got to be part of our low-level routines, right? Don't need that. Our low-level routines. What do our low-level routines like send and start give us? Yeah, they give us a status register value. So if we go back to our 328p data sheet, and I know which way to look, here we go. So let's go to the master mode for a second here. The difference between an acknowledge and a not acknowledge, 18 versus 20. Okay, so we'll know, we'll be able to check, or we can fly blind. We can basically say, all right, we're just going to assume everything has gone according to plan and that we got an acknowledge or didn't get an acknowledge as we see fit. All right, so that covers writing. That covers writing. Where are we? So reading is a... Oh, I've got to change the name of this to multi-write. I might not use all of these functions. I'm sort of working from a generic standpoint of what I might need. So I'm also going to build up a single read function. Single read uint8 underscore t. I'll start by copying it out. Might not be the smartest thing I've ever done. So obviously I'm not sending any data, I'm receiving data. So I wouldn't use it in the argument list unless I was passing by reference. What would I do instead? Probably. If I wanted to get data out of a function, what do I have to do in C? I can't declare it as void, I have to declare it as something else. Volatile is for interrupts mostly, and volatile is a modifier of a type. So you would modify for example, uint8 underscore t to be volatile. But this is what we're gonna read a single byte, and it's gonna be returned. All right. So how do we do that? Well, at its most basic, we've got to send a start bit or start condition and the slave address. But now we want to read, so that bit becomes a 1. Now, if I look at the data sheet, we have kind of a problem, because what I wanted to be able to do was send it some address and read from that address. Now, when I say address, I've got to be clear. This is my I2C address. ADDR is my register pointer address. So this goes inside of the DS3231. This is the DS3231. Okay, so that's a problem though, because I don't have the ability here to do that. If I wanted to do that, I think if I go down a little bit, it gets a little more interesting. All right, and this is actually kind of fun. This is one we might be able to do. So let's look at what happens. First, we send a start condition, and we actually do a write condition. So we send a write. Then we send the register pointer we want to read from. Then SR is a repeated start, where we send the same stuff, but now we say 1 for read. And then we get as many bytes as we want. And here's where things get a little bit more interesting, because now when we send things, the gray is us sending to the receiver. So it gets a little bit more complicated, because we have to choose whether or not to send an acknowledge or a not acknowledge. And the way we've set this up, if I go back to my thing here, this is send. There's not a whole lot here that's telling us whether or not we are sending an acknowledge. This doesn't differentiate between sending and receiving. So I may have missed a function. We can check that out. Let's go to the data sheet and see how we receive a byte. So we go over here. Let's look at, okay, our data packet we've seen before. Here's a typical transmission where we are writing. When we're reading, a little bit further on, here's our code, right, for writing. Come on, master mode transmit, master mode transmit, master mode receive. Further on. Did I skip over it? I must have skipped over it. The short answer is you have to set the bit. You have to set the control bit. I just wanted to be able to show you where it was in the data sheet so you could reference it. That's for writing. Does it not give you an example of reading? That seems a little odd. Master transmit, master receive mode. Okay, So maybe it doesn't give you source code for this. The trick here, let's look at it here, the status codes that you would receive. So as you receive things, you can send a start condition the same way. Okay, and assuming that you send the start condition and you send the slave address plus a receive, you can either receive an acknowledge or you receive a not acknowledge. Okay, and then, well, actually, let's look right here, or rather right there, where you've received the acknowledge. Let's look at our next steps. Okay, we've got to have the, oh, I got to zoom out a little bit. What do we have to do? Depending on if we want to send an acknowledge or not, we put a 1 on the TWInt, and if we want an acknowledge, we put a 1 in the TWEA bit. That's the one thing we haven't dealt with. That's our one function that we're missing. Okay, so I'm going to go ahead and say uint 8 underscore t. Actually, I'll modify this function. No, I won't. I'll make another function. uint 8 underscore t TWI receive. And now what I need to say, instead of giving the data that I'm going to send, underscore t star d, and I'm also going to say uint 8 underscore t ACK. What I've said now is I'm going to tell it whether or not I want to acknowledge the received byte, and this is where I'm going to put the data. How do I do that? Well, to start with, it's about the same. I say, all right, I'm going to write a 1 to that. I'm going to make sure I enable it. But what I'm going to do, depending on if I have an acknowledge or not, okay, I'm going to do the following. ORed with ACK equal to 0, question mark, 0, 1. All right. How many people is this the first time you've seen a syntax like this? First time. All right. This is what's known as a ternary operator. Basically, it's a condensed if-else statement. What I could have said is if acknowledge equals 0, do this, else do TW enable acknowledge, do that. But instead what I'm just going to say is that. These two options are equivalent. It's just saying either you're going to put a 0 in the TW enabled position or a 1 in the 0 in the TW enabled position. So depending on if I want to acknowledge something, it's just a shorthand version. Okay, keep things concise here. Now, other than that, that's it. That's all we have to deal with. We just sit there, we wait for the interrupt flag to fire. Now, however, we have to do one more thing. First off, we have to return that data. We're going to do that by saying star D, dereference, the value at the address of D is equal to the 2-wire data register. That's where the data is going to come in. Right? So we send data out by writing to the data register. We receive data by reading from the data register. And lastly, I'm going to return the same thing that I always return. I'm going to return the status register. So this is a little bit different. Okay, the limitations of C say I can only return one value. It would be nice if I could return the data and the status register, but I didn't. Okay, and so to keep everything homogeneous, all these uint 8 return values are always the status register. So if I want to receive a byte, I have to pass it by reference. Okay, so let's go back now and let's continue with this single single byte read. This is a random access read. Okay. So the question is, what do? I have to say TWI receive. Now, what do I have to give it? Well, I have to choose whether or not I'm acknowledging it. Is there any rule for whether or not I acknowledge things? Well, there's a note right here. The last byte is followed by a not acknowledge. Okay, so since we're only reading one byte, that's a 0, a not acknowledge. And I have to look at my order because I've forgotten. First thing is acknowledge. So I'm going to send a 0 for not acknowledge. And then I need to have a place to put it. So I'm going to have to create a temporary place. So I say, all right, send the address of temp so that inside that function, I can overwrite the value at the address of temp. And finally, I can return temp. Okay. So there's my single byte read. That's not too bad. It did require a little bit of background, though. Right? We weren't just able to use what we'd already written. So never be afraid to go back to your original library and say, shucks, I've missed something. Nothing that critical, is almost the same, right? But just a little bit different. So let's now tackle multi-byte write. Multi-byte write. Multi-byte read. So let's start by grabbing single byte read and let's augment it. We'll put it right next to multi-byte write. Okay, multi-read. Now we need to do a little bit more. So before we returned the data that we cared about. Now we're trying to return more than one byte of data. So I think we are stuck passing by address uint8 underscore t star data uint8 underscore t count. Now this is going to be a little bit different from the multi-byte write. Here we say write to this address this data, which is in an array, and this many bytes. Here we're saying read from this address, put the data here, read this many bytes. And so probably this is more of a void function. All of these are polite suggestions, okay? You can go to town with this. So to do I might have erred. I might have erred ever so slightly. I think my single byte read is a little bit off. I don't think I paid attention to the data sheet for the 3231 quite correctly. What I did was I did a slave address plus a write, and then a receive byte. Is that what I should have done? This is for a random access read. So what I did match up with this diagram. Supposed to write, then read. So let's go over this in terms of packets. First, slave address plus a write. Then set your register pointer. Did I do that? No, I did not. So I need to go ahead and I need to put my register pointer here. That's my address byte. So that's a write. Then what's next? What does SR stand for? Repeated start. So now I actually need to call that start function again. And that'll take care. So the start function will do starts or repeated starts, doesn't care. Okay. Then what's next? After my repeated start, I need to send another slave address. But this time, oh goodness, I've messed up everything. What does a 1 mean? That means a read. So this should have been a write, okay? and this should have been a read. Now, let's just pause for a moment. Let's say you do this. I'm not saying that any of you would ever make a mistake like this. But if you did, what would happen? So what did we do? Let's comment out the lines that weren't there before. We would send a start bit. Then we'd send this, and then we'd try to do this. Okay. Well, here's what's going to happen. We're going to send out that start bit, and this function does return a byte. So, if you are having a problem, first thing you should do is grab a status variable and make everything, every time you do anything, return a status byte. I've actually messed up even more ways. This gets even better, okay? So we're going to see what happens, all right? So we say start. Now, start is going to return one of two values. I even commented it. Maybe I didn't comment it. Oh, I commented it in the other library. Start returns one of two things, either 8 or 10. Those are the only two things it returns, either an 8 or a 10. 8 means it's a start, 10 means a repeated start. Now, first time through, it's going to return 8. Then you're going to try and send. And this will probably function correctly. Okay, it'll send a write. We've got to go to the 328p datasheet. Here we are in master receive mode, okay, which is not what we're doing. We're doing master write mode. So I've got to go to the other table. Here's master write mode. So I'll see either a 18 indicating an acknowledge or a 20. So probably the first time through I'll see an 18 because the DS3231 knows what happens with a write. But what the DS32 is expecting on a write is then the address pointer. What you are instead doing is saying, hey, you send me some data. Now, what will happen physically? This is a real good question. What will happen physically? Anybody have any thoughts on what might happen if you send out a receipt? Yeah.
We'll be stuck on the wait forever.
Stuck on the waiting for what?
For the person to send anything, but we'll be sending it, so it's waiting forever.
Well, so that's a question. We've got two lines on this bus, right? We've got a clock and a data. So, in all cases, who's driving the clock? Well, it was a trick question, right? There's 4 words we use to describe various players in this game. We've got master, slave. We also have transmitter and receiver. Okay, so when and let's go back up and look at these diagrams here. I want to go all the way. Oh, I'm in the wrong data sheet. I want to be here. Let's go look at those. Oh, I hope it gives it to us. Synchronization between multiple masters. Nope. That's just the generic. I may have to go to the slides to show you. So remember we had different book slides. I can't talk and open up slides at the same time. We had those things that were showing us the aggregate of an open drain line and also, come on. Yes, something like this. So we have the data line. Is that okay to see, everybody? Should I make it full screen? The aggregate data line and then the data from the transmitter, the data from the receiver. Here, this is the clock from the master. Okay? And in fact, all the time that we deal with this, the clock is driven by the master. Okay? When we do reading, remember, how does the peripheral say, I can't give you data yet? It does clock stretching. It pulls the clock line low to say, hey, I can't do this yet. But it still is being driven by the master. Whether or not you're the transmitter or the receiver. So your original answer of transmitter, or of master rather, was correct. Okay, but you can't just blindly say master instead of transmitter. You have to check. So where were we here? I want to be there. So we think, and we meaning the 328P, think we're about to receive data. So we drive the clock line. I want to be here. Okay, we drive the clock line 9 times. What do we see on the data line when we're clocking? Who's driving the bus right now? Who's driving the data line? We're expecting to receive bytes. The real-time clock is expecting to receive bytes. So everybody's expecting to receive. So is anybody driving it? No. If nobody's driving the bus, what is the voltage on the bus? I've heard nothing, which might mean Z stated. Is that what you... Okay, that's incorrect. Remember, this is an open collector output, which means it can pull to ground, but the rest of the time, and I might even be able to find a quick picture here. There it is. Okay. The rest of the time, there are pull-up resistors. So if it's not actively being pulled low, and that means actively driven low, they're pulled high. So, okay, everybody's expecting to receive data. So what does that mean? What are they receiving? What do they receive for their 8 data bits? All ones. What do they receive for their acknowledge bit? Yeah, a 1. Now, what does a 1 mean? A 1 is a not acknowledge. Okay? That means that we got to not acknowledge. So how does that translate for our DS3231? What does it see when it gets a not acknowledge? Well, it's always expecting an acknowledge when it's reading, or sorry, when it's writing. It's expecting to be acknowledged every time. It acknowledges it, right? It acknowledges it with a 0. Okay, because it's expecting to receive data. That's what's happening here. We're the receiver in this case. So it's going to pull the line low. Meanwhile, the 328P is expecting to receive data. And we also, go back to my data line here. What did we say? We said we were going to acknowledge it, bring it low. So we both decide to bring it low. Does that cause a problem? We're both trying to pull it to ground. No, it doesn't. It just, it goes low. Remember, whenever in doubt, think of the I2C data lines and the clock line as a balloon on a string. If 2 people pull it down, it's still pulled down. It doesn't matter that both of you are pulling it down. If one of you releases it, it's still pulled down. If the other one of you releases it, still pulled down. Only when both of you release it. So as far as both devices are concerned right now, they've both received a 7F, or rather a FF, with a not acknowledge. Now, that's the first time you're going to be able to tell that something has gone wrong. Okay, because you're expecting to receive a byte. Now, what happens when you're receiving a byte? You are the one who gets to play with an acknowledge here. Okay, so you look at your status bits. Okay, now if you miss this one, you're going to have to wait till the next time you do a read, because here's where things get interesting, right? First off, where am I in this sequence? Okay, first off, where does the peripheral think it is? The peripheral thinks that it's in write mode, and it thinks that it has gotten a pointer of 7F, or of 8F, of FF. So it thinks that it's right here. It's about to receive data bytes. Okay? When you come back into this function, what's the first thing you do? You say a start condition. Now, that immediately is going to tell this thing that it's totally in the wrong spot, because it expects start only here. The only place it actually sees a start condition is someplace over here in a repeated start. So that gets a little bit more interesting. Okay, so debugging through this, it's important to look at your status register bits. Even though when I'm writing these, it's not that critical to understand what should be happening. Okay, so now let's go through and fix these errors. First off, we need to follow along with what's supposed to happen. To do a random access single read, first we have to write the address we want to send to. Then we send a repeated start condition. Finally, we say, okay, I want to read from the device. So now we're here. Okay. Then we can do we can do our single receive. Say bring our acknowledge low to acknowledge it. Okay. However, if we're not acknowledging it, if it's a single byte read, we actually jump ahead to the last byte, which is a not acknowledge. Okay. The data is going to go into temp, and then we return temp. Yes?
Should receive start with 1,
It depends on how I wrote the receive function. So if I go down to the receive, if acknowledge is 0, it pulls it low. If acknowledge is not 0, it leaves it high. Or sorry, excuse me, I misspoke. If you put a 1 here, that is an acknowledge. So a 1 will enable acknowledge. But you're right, that's a bit of a confusing thing. So if I was writing this library, what I would probably do is define ACK and NACK. And then I would use that. So I'll say that an acknowledge is a 0, a not acknowledge is a 1. So down here, if it equals, that's going to be a bit of a problem. I can't have this be the same thing, right? So I'll call this argument underscore ACK. So if underscore ACK equals ACK, then send an ACK. Otherwise, send a NACK, a not acknowledge. Let's just make sure that I did that right, because this is where you got to check it. All right, so if the acknowledge bit is a 0, you send a 0. Let's collapse some of this stuff so I can see everything on the same page here. Okay, acknowledge is 0, send a 0. Okay, so I'm wrong. Probably it's going to be easier to just swap those. All right, so if you put a 1 in here, that means that you want to have an acknowledge, so you put a 1 in. That enables the acknowledge bit, and you're good to go. So now, when I call this function, TWI receive, I will instead say, instead of 0 or 1, I'll say NACK. Now it's totally clear. I don't have to worry about the 0, the 1, or am I enabling the 0? Am I enabling the 1? Is it active low? Is it active high? All right. So this is as you're building these library functions, what you can be doing. You have complete control. When you're using somebody else's library, keep in mind that they may have thought about some of this stuff. So before you go changing their library because you don't like the way they do it, they may have had a very good reason for doing it that way. Okay, so that's a single read. What else do we have to do? Well, at the end of this, we do have to send a stop condition, which is something I never did in my original single byte read. Okay, so that's probably the most complicated, with the exception of what we're about to do next, okay, which is the multi-byte read. So I'm going to take the code from this single byte read and start there. Now, we did start doing the multi-byte read already. We want to read from a particular address and this many bytes into that data register. So how do we go about this? First off, we do have to still do a write with the address, but then here we're going to do many bytes. So here's where things get a little bit more interesting. How do we go about doing this? Well, I know how many bytes I want to deal with. I'm going to put it in there now. There's a reason I did count minus 1. Okay. Oop, that goes outside. And that comment is no longer valid. So let's go back to that thing. Let's see. We do multi-byte reads by doing the slave address plus a write. Send the address. Repeated start with a read bit. As many bytes as we want, as long as we acknowledge them. And the last byte we don't acknowledge. So here, I'm going to acknowledge every byte. And what I'm going to do is I'm going to say data sub I. And that's all we're going to do. It goes into data sub I. Except because this is passed by address, I'm going to say address of data sub I. All right. Now, if I have a for loop that says for I equals 0, I less than 10, how many times will that loop run? 9, right? No, just try that again. I equals 0, I less than 10 will run 10 times. 10 times. If you say 10 minus 1, it'll run 9 times. So if I want to read 10 bytes, I put 10 in count, this will only execute 9 times. Why would I do it only 9 times? Why wouldn't I do it 10 times? Because the last byte is special. The data sheet tells me that the last byte has to have a not acknowledge. So what do I do here? Well, before I do anything, before I leave the function, I'll do one more read, and I will not acknowledge it. And that tells the real-time clock that I'm done. I can still use the variable I because it hasn't gone out of scope yet. And really, when the for loop exits, what will the value of this variable I be? Well, it'll be count. So there you go. Rather, it'll be count minus 1. So if I wanted to read 10, that would be address 9. So I would be 9, so this is sub 9. Multi-byte read, multi-byte write. All of this is kind of low-ish level stuff for the DS3231. We have not addressed any of the good stuff. Okay, talking to these registers. Where are we? We haven't addressed any of this good stuff here. So I'm going to leave it up to you to think about how you might want to deal with some of this stuff. So we've talked about how we might read different bits of this, how we might write bits to this. I have not told you anything about what these bits down here do, nor am I going to. Okay, it's up to you to read the data sheet and figure out which of these control bits you want to set, which are the status bits you want to poll. Some of this stuff is fairly self-explanatory: seconds, minutes, hours, day of week, date, month, year. Then we've got basically a repeat for alarm 1, a repeat for alarm 2 if you want to do alarms. Okay. And then the rest of this is random data and control and status. At a bare minimum, I can tell you that you might be doing the following. You've got I have here an unpopulated 7-segment display. Okay. This is the Mac 7221 chip. So it expects BCD values. If you're going to use decoding mode, you can do that. BCD values go into individual registers, 8-bit registers, just like the 3231 has, except it's over an SPI interface rather than I2C interface. It's usually very easy to tell them apart. I2C interfaces usually have some kind of clock and one kind of data. That's it. That's all they have. SPI interfaces have more lines. We've got slave in, slave out, or master in, master out, or MISO and MOSI, some variant on that. We have a clock line, and we usually have a chip select line. Not always. You really only need the chip select line if you're dealing with more than one device, okay? Although some devices will require that chip select line, even if they're the only device. The MAX 7221 is one of those. It needs that chip select line to latch data in. But there are some that you can just leave active all the time. You shouldn't, but there are some. Okay. So I made it through those routines, which is really the only ones I wanted to make it through. From here, I might go ahead and do a little bit of refactoring. One of the things I see a lot is this kind of weird stuff. So I might go back in here. I might say uint8 underscore t 2-wire interface slave address. All right, and I take the address that I want to talk to and whether or not I want to do a read write. And a read, remember, is a 1, a write is a 0. So I'll call the variable read, meaning if I put a 1 in, I want to read. If I put a 0 in, I don't want to read. So what do I have to do? Well, it's nothing that crazy. Where am I? Here. Nope, here. Every time it's something to the effect of this. Now this might not even be worth making into a function. Okay, this could just be a macro. Because really there's not a whole lot of interesting stuff going on here. Just returns the slave address. But it does, just like when I defined ACK and NACK, it makes things a little bit cleaner. Okay, it keeps that away. I can also add in some bookkeeping here. I can make sure that address is bounded by a 7-bit address. I can make sure that read is only a 0 or a 1. Okay, I can do it like that. So this could very well be a macro as well. It's not really doing a whole lot. I could have just declared it inline to tell the compiler, don't actually call this function, just put it in there without a function call, replace it. That would make my code size a little bit bigger, but oh well. Might be better for the speed gain. So now when I go through all of this, I can tweak all this out. I can just say TWI slave address SLA, and my address is OX68, and I want to write. Okay, there you go. And here I could actually even go one step further, and I could define 2-wire interface read as 1, define TWI write as 0. So now it's even closer to self-documenting code. 2-wire interface read. That's a read. Excuse me, that should be TWI write. Go through all of these. Okay, and replace them out. Makes it a little bit easier. For the actual DS3231, I would probably go so far as to define DS3231 address underscore address as OX68. Okay. While I'm on the subject of 68, 68 is the 7-bit address. Not all data sheets will give you the 7-bit address. They will give it to you as an 8-bit value, assuming that you're reading, so that you can just OR in that bit. In that case, if you were looking at this, let's go down to those, there we are. If you were looking at this, when you look at the logic analyzer trace, you won't see a 68 because 68 is shifted over by 1 bit. So what you'll actually see when you're, for example, doing a write, you'll see D0. that's what you'll see on your logic analyzer, okay, if you're doing decoding. And if I haven't mentioned this before, if you're in waveforms mode and you go to your logic analyzer, you can add an SPI bus or an I2C bus or a UART bus. If you want to add an I2C bus, you just tell it which DIO pin you've hooked up to data, which DIO pin you've hooked up to clock. And it will, I don't know if it'll actually do anything with this. Let's see. Okay, so this is just the simulation, so it doesn't have any I2C data on it. But it'll automatically label data and clock for you, and it will interpret all of what you're seeing. Yes?
Could you theoretically connect that simulator to the simulator of the Atmel? Or no?
Theoretically, yes. There is a scripting language associated with the waveform software, so you can shove stuff in from other places. I'm not quite sure how the scripting language in Atmel Studio works. I'm not sure. It's an interesting concept, though. I actually would like that. That would be very cool. Anybody looking for an honors project? No? That's a shame. That would be nice, though, if you could hook up your analog discovery to your thing. But you've got development boards you can hook up to it. While we're on the subject of development boards, book manuals. The explained mini manual. If you are looking for the I2C pins, you will not see any pins labeled I2C. However, if you look at the pin description on the 328P, okay, the I2C pins are pin C5 and C4, which conveniently exist both on the right side of the board, on the top right, and on the bottom left. So you can choose either connection. They're wired together. It's just they're in two spots on the development board. So that's your choice which to grab there. You can have it from either side. So that's it. You've got to interface the following devices for your final app. 7-segment displays, real-time clocks, the keypad, which I might have, that's okay, the keypad, 4x4 keypad, and the buzzer, I think, are as the bare minimum. Okay. In the lab, it does tell you you might want to consider different combinations of bits. You might have to rewrite your code a little bit for the button keypad, okay, depending on how you move things around. But that's what I got. Any questions on that? All right. If you're taking notes, you're welcome to use this code in thing. I haven't given away the farm here. It's just low-level code, okay, that you can start removing the need to deal with the low-level registers.